I'm Simon van Dijk. I work at Platform 45. I've been there for 2 months. Been doing Ruby for only a year, so it's really awesome to be up here. And yeah, I'm not the best programmer, but I hope you guys enjoy what I'm going to speak about. It's a little bit of AI, a little bit of what I feel when I program in metaphors, which is something really cool. So yeah, let's get started. So the birds and the bees. When a man and a woman... Alright. So the birds and the bees, I'm going to be speaking about AI. And this is something one of my friends said. And I laughed back at her because I thought it was completely ridiculous that she thought AI had anything to do with aliens, right? Yeah, I mean, that's completely ridiculous. But it's understandable. By show of hands, who of you guys know what CI is? It's not continuous integration. Okay, so CI means Computational Intelligence, and it's a branch of AI that's mainly like the software side of AI. And I don't actually want to spend a lot of time with this, but I do think it's important just to understand where CI fits into everything. Because people have this idea of AI that's like, it's robots, it's aliens, whatever. So AI can be divided into 2 really, really broad categories, strong AI and weak AI. And strong AI is sort of general intelligence. It's like, can we make a machine, hardware and software, can we make it do something that a human can do, like a high-level task? And then we get weak AI, which is like, can we make a computer identify between pictures and cartoons? Or can we make it identify a face or a cat or whatever? Weak AI can then be divided into old-era AI and new-era AI. So old-era AI is brute force. It's sort of deterministic. I program and I get a result, and it'll always give me the same result. And this old and new has nothing to do with the time that it was introduced. It's got more to do with the approach taken. So old-era AI is completely deterministic. New-era AI, on that hand, is where we arrive at computational intelligence. And it's totally non-deterministic, which means there's a lot of randomness in the algorithms. You'll never get the same result. But what this means for computation is if you're solving a problem, because the algorithm is not deterministic, you're never guaranteed to get a really good solution, or a solution that works in any way, which might be scary for like the formal guys, but I think it's awesome. So I've got these 2 Arduinos that platform gave me, and whoever can name these 5, actually whoever can name the most computational intelligence paradigms can get an Arduino. A Raspberry Pi, yeah, not like a eating pie. Seriously? Okay, one more. One more? That's right. What was that?
The 3 that they said.
Sorry, what did you say at the back there? What did you say at the back there?
Artificial intelligence.
Yeah, so dude, just come to me afterwards. You can get a Raspberry Pi. Cool. Seriously, it's right here. It's like pretty awesome. So we have evolutionary computation, which uses the metaphor of evolution, like Darwin's theory of evolution. and this is mainly used in optimization, but it's got lots of applications. Swarm intelligence is what I'm going to be speaking about today. It means there's complex behavior that emerges from simple units acting together. Fuzzy systems is just a system built on fuzzy reasoning. So if you guys know the Boolean true or false, fuzzy reasoning deals with you are 90% true or you are 50% false. This is really cool for knowledge bases where you can, with a knowledge base and rules, you can infer different decisions. Okay. But I won't go into that. Neural networks, the engineers love neural networks, right? And they're really cool, they're really powerful, they're predictive models. So you set it up, you train it on a data set, and it can make a prediction of maybe a classification, and it can predict more than one output, which is pretty cool. You can use it for a lot of stuff. Oh, sorry, I missed one. Artificial immune systems is the metaphor of the human immune system, how it determines between cells that are part of your body and cells that are not part of your body. Okay. And this is just to show these paradigms are sort of interconnected. There's a lot of overlap, and in the center is probability. So that whole non-deterministic thing that I spoke about, that's really at the heart of CI. And just before I get into what swarm intelligence actually is, speak a bit about metaphors. So we use this all the time. I think one of the oldest metaphors I know is like the idea of a desktop, because that was literally what they made it. It was your desktop on your virtual computer. It's such a cool abstraction. But like I get a lot of joy from typing these commands, brew tap, and then someone's GitHub repo, brew doctor. It's like, come fix me, whatever. Git blame. And the person who sort of pioneered this is Ada Lovelace, and she was Charles Babbage's lover. I don't know if they were actually married or whatever, but she said to Charles Babbage, the computer is not just a calculator. The numbers that you put into the computer can represent more than just numbers. You can represent scores of music with numbers. You can represent pictures, like all this cool stuff. So she's a bit of a hero to me. And programming joy, like I shared this thing that I wrote with Kevin, and it was really cool to listen to Matt and Kevin's talks about like how code is self-documenting and stuff like that. And I just love stuff like this, you know, where you can read it and it's like, yeah, it's doing that or whatever. Sorry.
You don't even need the begin block.
Sorry?
You don't even need the begin block.
Oh, really? Such a noob. Right, so what swallows do, this is an example of swarm intelligence now. What swallows do is they fly in this like homogeneous blob in the air, and the swallows actually never fly into each other, which is really cool. And there's no one swallow telling the next swallow like, hey, go left or whatever. They're individual units, they follow simple rules, and there's this complex behavior. Like the swarm doesn't just stay like a circle that moves in the air, it sort of goes like this, right? Ants, there's no king ant, right? There's a queen, but there's no king. The ants act individually, but they can do really complex stuff like cross bridges that are longer than themselves. They can even make bridges cross water, whatever. And the idea that comes out of this is complexity from simplicity, right? And this is a really cool example. Conway's Game of Life, there's such simple rules, but the incredibly complex behavior that comes out of those rules is a little bit of what swarm intelligence is about. I actually found out someone wrote a Turing machine in Conway's Game of Life. Like, isn't that crazy? That's totally crazy. So these individual units, they communicate on another level. Not like another level, but there's no central communication. So this is an example. If you imagine the arrows as swallows and the direction that they're traveling in and the length as their trajectory, the red arrow is the swallow we're talking about. It can observe its neighbors and it can make a decision on where to fly. And this has actually been proven mathematically. Swallows look at the birds around them, and they know if I go this way, I'm not going to fly into my neighbor. So how does this translate to like actually doing real work? Because you think I'm talking about like animals and stuff. This is weird. Let's first talk about what ants do and how it can actually help with data clustering. Ants do this thing called cemetery formation. So if you can imagine a petri dish and those black dots as dead ants and the green dots as live ants, what the ants do is they pick up the dead bodies and they put them in piles. This is mainly to remove the dead bodies from the hive because the bodies emit a toxin once they're dead. So it's a little bit to protect the queen, but also to help decompose like their waste and stuff. So what they do is they pick up a dead ant, they walk around a bit and they smell a bit more toxins over here because there's dead bodies in that direction. So they put it down. Then they get up, go find another ant, pick it up, they smell more toxins, they put it down. And what happens is they move these items into clusters, right? Just really quickly what data clustering is. If you can imagine a number line, and these are integers, and imagine a cluster, there exists a cluster around 8. So numbers 7 and 9 might be considered part of that cluster because they're similar, okay? They're really close. But numbers 4 and 12 would be considered maybe part of a different cluster, depending on the size of the clusters. And this is just simple data, it's a number, but if you can imagine something more applicable like a product and you want to identify groups of products that you can market to the same kind of people or whatever. So we can define a cluster as a subset of a data set, and in this case, D1 and D2 are just numbers. The cluster is all the numbers in the data set that are similar to the middle of a cluster. Okay. But there's problems. The data set is really large. This is sort of an old era AI approach. It's like, let me brute force it or whatever. But the most important part is actually we don't know the cluster centroids. That's what we want to know. We want to know how are these groupings made so we can use the information for like business purposes or whatever. So let's start off with a model. If you can imagine the petri dish as a grid that's circular, so if you go off the grid, you come back on the other side. And on the grid, we have these guys, which are the data. The users have interests, and an interest in this case is just simply an array of some type. Okay. It's a little bit of a contrived example, but I think it hits home. Everyone knows what a user is, that sort of thing. They have one behavior, which is they are able to determine the similarity of themselves with another one. An ant will show as a green star for no particular reason. Ants have 3 behaviors. They can perceive the environment around them, like that. They can act on the environment. So if they walk on top of a body, they'll pick it up with some probability. And if they're carrying a body, a body is an item. And if they're carrying a body and they walk into an empty grid area, they will drop it with some probability. Okay. And then that's the acting part, and obviously they can move. So every iteration of this algorithm, they move one slot. It's probably important to note right now that there's a rule imposed on the grid that you can't pile an item on top of one another. You can relax this rule. It's just something that we put in so you can see the items together instead of on top of each other. And seriously, guys, this is the algorithm. It's so simple. The power is in the metaphor. It's not really in like insanely complex data structures or algorithms or whatever. The power is in the metaphor of simple units acting together to emit this complex behavior. So you begin by putting items on a grid, and the grid can be any shape. Then you put the ants on the grid. You normally have about 10% of the grid size full of items, and you have only about 10% of those items as ants. So you have very, very few ants, but you run the algorithm continuously, and the ants walk around, pick up items, put them down, it's pretty cool. Because in AI, one of the things that detract from using neural networks, which is used everywhere, is your data is like a data stream, which is really cool. With your functional data, that's stuff that the guys spoke about yesterday. It's not the same as it was yesterday, and if you can keep track of that, so the interests change. So you can imagine why having an algorithm that you can just run all the time instead of rerunning it is advantageous. So for as many iterations, maybe forever, if it's a worker or whatever, you tell each ant to perceive its environment and act upon it, and we'll talk about the probabilities. And then you tell each ant to move. If it's got an item or not, doesn't matter, it needs to move. The ant looks around it, it checks, it computes a value that tells it how similar the item it's carrying is to the items around it, or how similar the item that it's on top of is to the items around it. Then, with a probabilistic function, it generates a random value between 0 and 1, gives the function the similarity, and then it either picks it up if it's unladen, so it doesn't have a dead body or whatever, and it drops the item according to some probability if it's carrying one. Right. And these are just the probabilities. I mean, these are just math functions. You can swap them out to whatever works. I wasn't actually going to show this because it's not really important. It's just maths, right? I made a mistake on the slide. The one under pickup probability is supposed to be a variable. It's supposed to be lambda pickup, and those can be tuned according to what sort of probabilities you're getting. Okay, and then obviously the ant and the item have these two methods that are really simple. I'm not even going to show them. And yeah, this is really it. The result is that the ants pick up the items, and if you can imagine an ant that is sort of in a desert, there's no items around it. If it arrives there, it's going to look at the items surrounding that ant. Similarity is going to be very, very low because there's no items, and the probability then will be very high that the ant will pick up that item that's in the desert. Then it'll randomly walk. Maybe it arrives by a cluster, and then it computes the probability of dropping the item, because it has one now, and it looks at the items around it. The probability of dropping the item will increase according to the similarity, and it'll drop the item in that area. So the result is you get these clusters of similar items, and the clusters are separated. If you imagine the users, you have music, food, tech, or whatever interests, and you'll find the items that are grouped together have more interests than the items that aren't. Again, this is a bit of a contrived example because the model is so simple. If you had maybe more complex data, you can imagine it in a real-world scenario. So that's really it. I love the Ruby Rogues podcast. So these are my picks. There's a 7-minute talk about how ants bury their dead on NPR. There's a 2-minute talk if you don't have that much time. Seriously. It's like 7 minutes. Ants and their dead. And then the platform guys are going to hate me for this, but I love workflowy.com, and I don't care what you say about it. It's really cool. It's like a list app. Yeah, so thanks, guys. Do you have any questions? Yeah.
Yeah, so when you do the clustering, does it converge in the end, or like is the risk of like local maximum where there is like a better clustering, but it's all okay now, so and you won't move it to like different clusters?
Not really, because the similarity heuristic determines where the ant will go. Maybe if an item's like on the borderline, it might be placed in an area, and then it could fall into a local minimum like that, because then the probability won't be that high to pick it up and move it. But yeah, because you continuously run it, it gets more chances of an ant walking over it and trying that probability. So it's pretty cool that you can just continuously run it. Because there's always exploration, you know. The ants are always moving around the grid.
So it would after move and I draw an existing cluster and put it in a cluster.
Yeah. Yeah, because, I mean, what it's doing, it's also doing the fuzzy systems thing, like no data item is strictly part of a cluster. It's part of a cluster to some probability. Yeah. Does that answer your question? Alex?
So do you think you can use this to segment e-commerce sites users into certain groups that you can market to?
Oh yeah, for sure. Yeah, I'd be a little worried with this algorithm, maybe with the size of the data, but it's pretty easy. You just segment the data and then run the algorithm. You can throw them together, mix them up, and then you can get sort of the clusters together. Yeah. Again.
One more. So is it, this algorithm is it independent in using a grid?
No.
Or could you use just single dimensional system to place that you group by?
Yeah, you could. You could use that.
Is the difference in like performance, like precision, the more dimensions you have, or?
I have absolutely no idea. But it's actually a good point. The idea of having a one-dimensional grid or two-dimensional grid or a hypercube where the dimensions are connected in some way, I'm sure you'll actually get much better results because the ants can move in a uniform manner from one position to another position. So there's no bias in terms of where they're initially placed.
But if I can just throw my head in on that question, in stochastics, the true value comes in when you have more than 3 dimensions, because then you start getting answers that you can't imagine. So for everything you want to know, you should have a dimension. Like on that thing, you would probably want to rate people according to a certain two axis. So, you know, there would be 2 things you evaluate against each other. The ants would place them in a certain category.
Okay,
But
so
if
you
you
have
had
one
like,
dimension for like music, one dimension, movies, one.
well, that could be what you base decisions on, but you might want to know if there's somebody who will spend a lot of money or not, or something like that. So, but like in stochastics, and we use it in mechanical engineering or structural engineering, you might have 1,000 parameters that you want to evaluate, and that's where these things come in very nicely.
Yeah. Another cool thing is that a lot of people use, for the similarity function, they don't use an explicit function that calculates an absolute value. They use predictive model. So they'll take a subset of the data set and they'll train a neural network where they have the target values of this user is interested in this stuff. And then they'll train a neural network model to predict, given a random user, what they are interested in. So you don't necessarily even have to explicitly program a similarity function. You can literally train an artificial brain to do that for yourself. Yeah, sorry, it's quite heavy on the AI, but I hope you guys really get like how you can get joy out of programming with metaphors and ants and stuff.
Have you done anything in a highly concurrent application?
No, I haven't, but that's actually a really interesting point. Because there's... I have no idea. Yeah. Yeah, I guess it could work. No, I haven't. It's actually a huge field in AI where all the algorithms are single-threaded, and it's because of the distributed nature of the algorithms, they should be, you know, pushing into parallel stuff. Ivor?
The grid, is that a metaphor, or does it actually represent values on the scales that you're comparing on? So, yeah, I mean, is it quantitative or qualitative things? You know, is there a continuum?
The grid?
Yeah.
Do you mean if an item is in a position on the grid, does it say anything about the item?
Yes.
No, absolutely not. Yeah. No, the grid is just to separate the items. The items carry, their value, whatever.
Right, so you don't need n-dimensional grid. You just need
No, but that was a good idea that you pointed out. It's less bias for an ant to move from this position to that position.
I was just interested because it's a simple model. Is there like a good strategy for tuning those parameters?
Again, I don't really know. This is actually a new algorithm to me. I've written a lot of particle swarms with swallows, but I haven't really written a lot of ants. I did this algorithm with homogeneous data, so they could just be placed in any grid, in any cluster. Yeah. Sorry, dude.
Yeah, because just in reference to convergence, I think you would want to use an even grid, so you'll start with very generous probabilities and then
Yeah.
bring them down.
Yeah, it's definitely a good idea to make them self-adaptive, the parameters. Cool, guys. Thanks.
No come electro por la vida.